It quickly tells you how many carbons there are in a sugar because you just count up the number of moles of the total. And then it tells you if you get CO2, it's a ketose for sure. If there's no CO2, it's an aldol. So it's used in this way. Okay, let's have a break.
The Lord up above.
We have learned 3 oxidations. Bromine in water oxidizes the aldehyde only. Nitric acid oxidizes top and bottom to the dioic acid. Watch out for symmetrization. And finally, you can chop the living daylight out of the sugar and chop it into individual single carbon pieces of use in determining how many carbons are in your sugar. So is it a tetrose, a triose, a hexose? And is it a ketose or is it an aldose? Okay. Now let's look at reduction. Reduction is actually simpler because we are not learning a new reagent. Reduction is simply reduction of the aldehyde to the corresponding alcohol. And lo and behold, we use the same reagent that we've used previously, a reagent that's perfectly suited to do this because sodium borohydride is stable in alcohols. In fact, you use it dissolves in methanol, and you use it in alcohol solution to do reductions of ketones. That goes back to chapter 8. Okay. And that's the beauty of sodium borohydride. It's relatively unreactive, and therefore the protons of an alcohol are not protic enough to make hydrogen, to attack the H- on borohydride. And so therefore, it doesn't care about all these hydroxy functions on the sugar chain. It just goes right after the aldehyde and turns it into the corresponding alcohol. Notice that this reduction also potentially symmetrizes the sugar, okay? Because now both top and bottom are hydroxymethyl. So again, if all the OHs are arranged in such a way that you can put a mirror plane through the molecule, then in fact that alcohol would be achiral. Okay? The name for these is alditols. Okay? So we've done aldonic acid, aldaric acids, and now alditols for the guys where the aldehyde function is reduced. So you may ask, well, wait a minute, this guy isn't there. It's really all this. For glucose, for example. And the answer is yes, it's all this, but it's in equilibrium. So it's a classic Le Chatelier's principle over again. Sodium borohydride reacts only with a minor component in the equilibrium, but by pulling it out of that equilibrium, reacting it further to something else, it completely shifts the equilibrium from left to the right. Classic case of that. So this guy, according to this nomenclature, would turn glucose into glucitol, but there's another common name, sorbitol. Again, sorbitol is also known as sugar alcohol. It's actually used as an artificial sweetener. Some of you may have heard of sorbitol. Sorbitol has lower calorific content than normal table sugar, which is actually ether bridged dimer formed from glucose and fructose. We mentioned that before. I'll show you a structure at the end. So it's 2.6 calories versus 4 calories per gram. And the sorbitol also occurs in a bunch of fruits. Okay. So here's the symmetrization that also ties in ketoses with the isomeric aldoses by reduction. Namely, if you look, we did this a lot with glucose and fructose, they're isomers, but this is true for all of the sugars with the same carbon number. The ketose form and the aldose forms, they're isomeric. So in the 4-carbon chain, this piece is called erythrulose, is the ketose, and there are 2 aldoses, they're isomers of that ketose, they're called erythrulose and threose. If you reduce this guy, there's no stereocenter here, but you're introducing one in the reduction. So in the ketose case, reduction gives you 2 new diastereomers. In the Fischer stencil, beautifully easily shown, you just make another cross, and one OH is to the right and the other one is to the left. Those are the 2 compounds. You don't have to worry about RNS or anything else. That's 2 different compounds. And you notice that the one on the left is actually achiral. So there's symmetrization. There's a symmetry plane. This one is chiral. These 2 are also formed when you start with erythrose. You get this one. With threose, you get that one. So you can correlate the aldose form with the ketose form of a sugar chain by reduction. Okay? So these kinds of relationships show up in exams. Okay? So all you have to do is keep track of your Fischer projection and then see what you get and compare and see whether they're mirror planes or not. And that's very simple problems. In fact, I think this slide is out of one of the final exams. Okay. What about esterification and ether formation? Old chemistry. And it works. There's just the twist of sugar chemistry because there are a whole bunch of these hydroxy functions. So selectivity is an issue. So you can't selectively make, if you're just looking at esterification, make an ester at only one OH function. That's selectivity. is very difficult to attain. So instead, organic chemists do a blanket esterification. So you treat the sugar, which exists primarily in the cyclic hemiacetal form, back to glucose, with an acetylating agent. And here it's actually important that you don't use acetyl chloride, which in principle you could, because it gives you poor yields, because it makes HCl. HCl plays havoc with all these secondary alcohol functions. Remember, secondary alcohols, proton, you turn OH into a leaving group, you get carbocations. And carbocation anywhere in a polyol like this asks for tremendous trouble. So you don't use that. Instead, you use the milder acylating agent of the anhydride. So if you want to acetylate, which is typically what's done for protection purposes, you use acetic anhydride. And you use a little bit of pyridine, which is the nitrogen heterocycle that's slightly basic, to mop up the acetic acid, which is the leaving group in the acetylation. So basically buffering the solution. Don't have to remember that. All you need to know is acetic anhydride. And you get complete esterification. Every single OH is capped off in very high yields. You can do the same thing with methylation. You can use Williamson ether synthesis and methylate every single OH in your starting material. So you can use sodium hydroxide methyl iodide. In this particular prep, they used dimethyl sulfate, which is an even hotter methylating agent than methyl iodide. You, I think, should have seen this before. We haven't used it much. It's basically sulfate is a superb leaving group, even better than iodide, right? So it's just a dimethyl ester of sulfuric acid. Right? So you can use methyl iodide if you don't want to remember another reagent. And it will cap off all the OHs with methyl to make the corresponding methyl ethers. Notice that what happens at this stereocenter here, which is the hemiacetal stereocenter, you're turning the hemiacetal into the full acetal in this. Meaning that you're now locking that carbon. When it's a full acetal, it's no longer in equilibrium with the open chain form, okay, because the OH is gone. Okay? It's locked. So then now it's just one compound, it's fixed the way it is. And therefore these kinds of sugars are often called non-reducing because they're not in equilibrium with the aldehyde form that can be oxidized. Okay? So there's a beautiful aspect to this specific carbon because it is an acetal or hemiacetal carbon. It's much more reactive than all the other carbons in the molecule. So when you have completely methylated all of the OH functions, the acetal carbon, can be hydrolyzed under much milder conditions than would be required to hydrolyze the ordinary methyl ethers, which are very difficult to hydrolyze. You need concentrated HBr, which in this molecule would destroy. Okay? So after complete methylation, you can now liberate this carbon, very mild conditions, because it's an acetal. It's the classic acetal hydrolysis, mild, dilute, aqueous acid. Here in this experiment, they use 8% HCl in water. Okay? And what happens? You hydrolyze here and you get the OH. Okay? And this now is back to a hemiacetal. It's in equilibrium with the open form, which is the hydroxyaldehyde form. Okay? So that can be reduced again with sodium borohydride because it's in equilibrium with the open form. The corollary of this is, of course, that in the unprotected system, the hemiacetal function is much more reactive than the other OH function, so you can play with that selectively without touching the other OH function. So, for example, this guy, again, glucose, so it's the two glucopyranoses, OH up and down, the mixture that we get. If you treat that with acidic methanol, the classic conditions under which we normally formed acetals, namely acidic alcohol on a ketone, gives you the acetal. Acidic methanol on this hemiacetal gives you the full acetal. And of course, OH, the methoxy can come in from underneath or from the top. So in this case, you get a mixture of those two compounds. But again, that carbon is now fixed. Okay, it's no longer in equilibrium with the open chain form, and so no more equilibration with an aldehyde form. So you can treat this guy, for example, with strong base or with lithium aluminum hydride or something like that. Any reagent, it won't affect any reaction because the aldehyde is gone. Okay? And with this in place, this molecule, therefore, no longer, for example, undergoes mutual rotation in all the aspects that are associated with being in equilibrium with the open form. So you can selectively protect this carbon here as the acetal, and then do other chemistry on the other alcohol functions. And then finally, we can also, of course, protect the diol arrangements along the sugar chain as acetals by using a ketone. And in this case, the simplest ketone, the cheapest one, is acetone. So this is now the counterpart to making a cyclic acetal in order to protect a ketone. That's what we saw in chapter 17. We could protect ketones by taking ethylene glycol, for example, or a dithiol, a sulfur analog. With acid, it made the cyclic acetal. And the reason there was the purpose there was to use a cheap diol, ethylene glycol, to protect an expensive ketone, which we wanted to elaborate further. Here the goal is to use a cheap ketone to protect the expensive diol, namely the sugar. But the process is the same. They protect each other. It's mutual protection. And so that's the genetic process. And so you can do this for a bunch of these cyclic hemiacetal functions. And crucial, of course, since it's a cyclic, in the case of cyclic acetal formation like this, 5-membered ring, is the OHs have to be in the cyclohexane stencil of the cyclic sugar, have to be cis to each other, meaning that they have to be reachable. And remember, in the cyclohexane stencil, neighboring cis configuration means always that one of them is equatorial, the other one is axial. It's kind of indicated here. This one's equatorial, it's cis to this one, but because of the peculiar features of the cyclohexane chair, this one is actually axial. Okay? And it's if the OH were to be here, that actually would be the trans conformation. So they're most easily reachable in terms of making cyclic acetals when they're cis. So this cis diol and cis diol are easily reached and capped off with acetone. So this guy with a little bit of acid and acetone will turn into this bis acetal, often called acetonide because it's derived from acetone. And that protects the basic framework quite nicely, leaving intact the hydroxymethyl that's dangling here. And typically that dangling hydroxymethyl is the last one to go because it's the most costly to harness in a cyclic acetal function. You can even see that in this molecular model. The hydroxymethyl at the end has the most degrees of freedom to rotate around. And so entropically, harnessing that is more costly than harnessing any of the other OHs. So that's typically left untouched by this acetal formation. Not predictable for you. And so I won't give you a problem where I say, throw a sugar at you and say, make the cyclic acetal. Well, this is structure. Okay, I'm not going to do that. I will ask you to recognize a cyclic acetal of sugar and possibly make you hydrolyze it to get the free sugar or something like that. And so along the lines what you see in the practice exams. And that's as far as we want to go today. Thank you. Have a nice weekend.